Okay, so the first thing that we're going to do in rational functions is define what a rational function is. A rational function is a function that's a ratio of two polynomial functions. And as you recall, what makes a function a polynomial function is that all the exponents are whole numbers. So if we take a ratio, so we put in the numerator of a fraction a polynomial, and in the denominator a polynomial, then we get a rational function. And it is by the nature of fractions that the denominator, that q of x, that function that's in the denominator, cannot be zero. You can never have zero in the denominator of a fraction, ever. So by the nature of how a rational function is defined, you have or may have restrictions on the domain of this function. Q of x cannot equal zero. So when you're looking at a rational function, you may have to restrict the domain in such a way that the denominator cannot equal zero. And we'll look at that in just a second. Okay, the next thing we need to define are vertical asymptotes. So rational functions may have these things called vertical asymptotes. And what is a vertical asymptote of a function? Now, this precludes how you find them. We'll look at that in the next slide. But what does it mean that a rational function has a vertical asymptote? Well, what it means is this is a vertical line, straight up and down, that your function approaches, but it can't cross it. It can't touch it. What does it do? What behavior does your function have at this vertical asymptote? Well, it has end behavior. So either the function increases without bound as it approaches that vertical asymptote, or it decreases without bound as it approaches that vertical asymptote. So we have four pictures here of this behavior. In the first image on the left, I have a function that's approaching that vertical line from the positive direction. And that is denoted right here as x approaches, as this function approaches that vertical line from the positive direction. So since the equation of that line is x equals a, as x approaches a from the positive direction, that's what that superscript plus means. Then what does that function do? It increases without bound. Y goes to infinity. So as we're approaching from this direction here, it approaches, it approaches, it approaches. It can't cross, it can't touch, it increases without bound. Now this next graph to the right, we're showing a graph that's approaching from the negative direction. And that's what that superscript negative means. As x approaches a from the negative direction, then what happens? As the graph is approaching that line y equals a, it can't touch it, it can't cross it, it increases without bound. So just like in the previous graph, we're approaching from the negative direction, we can't cross, we can't touch, we increase without bound. Now the second two graphs demonstrate decreasing without bound. Again, your graph cannot cross or touch, excuse me, a vertical asymptote. So what does it have to do? It has to skim it, and it skims it by either going up or going down. So the first graph shows as we're approaching from the positive direction. So again, oops, as x is approaching that line y equals a from the positive direction, then it can't cross or touch that vertical line, so it skims it. And in this case, it decreases without bound. And the same is true in the last graph on the left. Excuse me, that's right, right? As x is approaching that line from the negative direction, it can't touch that line, can't cross that line, it decreases without bound. So vertical asymptote is a vertical line, x equals a constant, that your function approaches, can't cross, can't touch. It either increases without bound at that line, or it decreases without bound at that line. Okay, how do you find these things? Well, given a rational function that's a ratio of two polynomial functions, so the numerator p of x is a polynomial function, and the denominator q of x is a polynomial function. If I cancel any common factors in the numerator and the denominator of this function, cancel those. Whatever I have left in the denominator, whatever factor I have left in the denominator, if I set that equal to 0, that finds the vertical asymptotes. Okay, so you have to factor your numerator, factor your denominator, cancel any common factors if you have them. Once it's in its reduced form, set the denominator equal to 0, and that gives you an asymptote. And that kind of sort of makes sense that that's something like that, because denominators can't equal 0. So if you set the denominator equal to 0 and you get a value, something has to happen at that value, because the domain is not defined at that value. You cannot have a denominator equal to 0. That's a restriction on the domain of your function. So what is it? It's an asymptote, because your function cannot equal that value. It either increases or decreases without bound at that value. It cannot equal that value, okay? So let's look at this rational function. So if we look at this rational function, I first need to factor that denominator, because I need to make sure there's nothing I can cancel with the numerator. And it also sets me up for setting it equal to 0 and finding the asymptotes. So I'm going to go ahead and I'm going to factor that denominator. And that is the difference of two squares. The first term is a perfect square. One is a perfect square. One is a perfect everything. So I can factor that to a sum times a difference, because a sum times a difference, when I FOIL it, outside plus inside equals 0. So we're going to go ahead and factor that to x plus 1 times x minus 1. And that is the factorization of x squared minus 1, outside plus inside equals 0. So then I look, are there any common factors that I can cancel? And the answer is no. In the numerator, the factor is x. In the denominator, I have two factors, x plus 1, and another factor, x minus 1. Nothing cancels. You cannot cancel an x. Can't do that, because there is no x factor in the denominator. So that is in reduced form. So the rule says if it's in reduced form, I don't have anything I can cancel, set the denominator equal to 0, and that will give you the vertical asymptotes. So I'm going to do that. Set each factor equal to 0. So I get either x is -1 or x is +1. So this thing has two vertical asymptotes. One at -1, and you do need to write these as equations. X equals that constant and x equals +1. Now, if you were to graph this, which I highly encourage you to do that, you have a calculator that graphs quite nicely. I highly encourage you to graph all of these. Let that be the first thing you do. Go ahead and graph it. What's this thing look like? Well, this is what the graph looks like. So I found that it had vertical asymptotes at -1, x equals -1, and x equals +1. So what does my graph do? All sorts of stuff. As we're approaching the asymptote at x equals -1 from the negative direction, so as we're approaching, x is approaching -1 from the negative direction, we decrease without bound. Y goes to -infinity. In between those two asymptotes, as x approaches from the positive direction, as it approaches x equals -1 from the positive direction, it increases without bound. So in here, it's increasing without bound. As it approaches the asymptote at x equals +1, it decreases without bound. And then as it approaches the asymptote at x equals +1 from the positive direction, it increases without bound. So we have that behavior that we know we should have at those two vertical asymptotes. The graph of our function either increases or decreases without bound at each of those asymptotes. All right, how about this function? I have f of x equals x minus 2 over x squared minus 4. So again, I'm going to factor this. The denominator factors to x plus 2 times x minus 2. So I do have a factor that will cancel. I can cancel the x minus 2 because it's a factor in the numerator and it's a factor in the denominator. So I can cancel that. So x minus 2 divided by x minus 2 is 1. So in the numerator, I have 1. And in the denominator, I have x plus 2. So now that this function is in reduced form, I can set the denominator equal to 0 to find the vertical asymptote. So I have a vertical asymptote at x equals -2. But wait a minute. I canceled from the numerator and the denominator x minus 2. What if x is equal to 2? Well, it can't. It can't equal 2. So 2 is a restriction on the domain. The vertical asymptote is a restriction on the domain. X cannot equal -2. Your function has behavior at -2. It either increases or decreases without bound as it approaches -2, but it can't equal -2. It can't equal 2 either, but 2 is not an asymptote. What is 2 then? 2 is a hole in the graph. Literally, it's a hole. So several semesters ago, a student said, so the factor you cancel, that's the hole. The factor that's left over in the denominator, that's the asymptote. And that sums it up. So anything you cancel in the numerator and denominator, that could be a hole in your graph. So x cannot equal 2. It can't, or you'd have a denominator that's equal to 0. You can't do that. So in this case, since we canceled the x minus 2, we're actually canceling 0 over 0 at x equals 2. I can't do that. So there is actually a hole, a physical hole in the graph at x equals 2. Now this is difficult to see when you graph it on your graphing calculator, your TI-84 calculator. it shows up much better on Desmos, which I like Desmos a lot. And I wish I could let you use it on exams, but it has so many features that enable you to do problems without actually knowing what you're doing. So I have to restrict your use of Desmos. But on homework, if you want to look at this using Desmos, I encourage you to do that. Because when you graph this on Desmos, which I have covered it up with my writing, you can see the behavior that we're talking about. We do have a vertical asymptote at -2. So let's draw that in with a different color. So at -2, I have vertical asymptote. I have to put my glasses on to see what I'm doing here. But I also have a hole, and that's kind of hard to see, but Desmos actually says at 2, this function's undefined. So x cannot equal 2. That's an actual hole in the graph. But you can see the behavior that we're talking about as we're approaching that vertical asymptote at x equals -2. As we approach it from the negative direction, we decrease without bound. As we approach it from the positive direction, we increase without bound. But since 2 is a restriction on the domain of my function, I actually have a physical hole at 2. So x cannot equal 2. If you graph this on your calculator and you use the table function on your calculator, so hit the table button, you will see at 2, you're going to get y is undefined. So it will actually tell you that y, f of x, does not exist at x equals 2. So give that a try. Graph this on your calculator, and then it should tell you that it's undefined at 2. It will also tell you it's undefined at -2, which is the asymptote. Okay, what are horizontal asymptotes? Horizontal asymptotes are different, completely different. So maybe they should have given them another name. Okay, it's still a line that your function approaches. So it's horizontal. Vertical asymptote is a vertical line, horizontal asymptote is a horizontal line. But it's a value that your function approaches as x increases without bound. So it's a y value that your function goes to as x gets infinitely big. And your function can't cross this line. It can go above it and then come back down. But eventually, as x goes to infinity, y goes to this value b. Okay, so it's a value that y approaches as x increases without bound. Right, how do you find horizontal asymptotes? Where these are the rules that you have for finding horizontal asymptotes. And these rules are in the notes that I provide for you for chapter 3. So if you'll go to Blackboard, course content, chapter 3, if you'll open those notes, you'll see these rules are listed along with a whole bunch of other stuff. Okay, so what are the rules? Given a rational function where we have a polynomial of degree n in the numerator, so the largest exponent in the numerator is some number n, and you have a polynomial function also in the denominator, and the degree of that polynomial function in the denominator is m. So the largest exponent in the denominator is m. Then compare the degree of the numerator to the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, this is number 1, then the x-axis, or y equals 0, that is the equation that describes the x-axis, y equals 0, is a horizontal asymptote. So if the numerator's degree is less than the denominator's degree, as x increases without bound, as x goes to infinity, then y goes to 0. And we'll demonstrate that here in just a minute. If the two polynomials in the numerator and denominator have the same degree, then you need to use the leading coefficients to find the horizontal asymptote. So if the degrees are the same, then the line y equals a sub n divided by b sub m is a horizontal asymptote. So a ratio of the leading coefficient of the numerator to the leading coefficient of the denominator is the horizontal asymptote. And if the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Okay, so let's look at this rational function. We have f of x equals 9x squared divided by 3x squared. So to determine if this function has horizontal asymptotes, I need to determine the degree of the numerator and the degree of the denominator. So looking at the numerator, the largest exponent, the only exponent, the largest exponent is 2. So the degree of the numerator polynomial function is 2. Now look at the denominator. The largest exponent in the denominator is also 2. So the degree of the denominator function is 2. And now we compare those. Is one bigger than the other, or are they the same number? And they are the same number. So since the numerator's degree equals the denominator's degree, there is a horizontal asymptote. And it is going to be y equals a ratio of the leading coefficients. So the leading coefficient in the numerator is the constant that you're multiplying times your variable of highest degree. So there's only one term in the numerator. So the leading coefficient in the numerator is 9 because you're multiplying x squared times 9. And the leading coefficient in the denominator is the constant that you're multiplying by the variable of highest degree, and that's 3. So the leading coefficient is 3. So our horizontal asymptote is y equals 3. And yes, you do need to write that as an equation. It's the horizontal line, y equals 3. Okay, I'm going to take a sip of coffee, and then we're going to pause and ponder for a moment. Let's ponder the behavior of this function as x increases without bound. So as the value of x gets bigger and bigger and bigger and bigger, what happens to f of x? Okay, what happens as x gets bigger and bigger and bigger? Well, the numerator gets infinitely large. It gets infinitely large 9 times some really, really big number. And what happens in the denominator? As x gets larger and larger and larger, who cares about the plus 1? Let's say x is 10 million. So you have 3 times 10 million squared plus 1. It becomes negligible. So as x increases without bound, that little old plus 1 down there, nobody cares. So if you take the ratio of 9 times 10 million squared divided by 3 times 10 million squared plus 1, you approximately get 3. So as x gets infinitely big, y approaches the value of 3. And I covered up the graph with writing, but you can see as x goes towards infinity in the positive direction, this function is approaching the value of y equals 3. Okay, how about this one? So what's the numerator's degree? There's an understood 1 there. There's a 2 in the denominator. That's the largest exponent. And so now we compare the degree of the numerator to the degree of the denominator. And the numerator's degree is less than the denominator's degree. 1 is a smaller number than 2. So if the numerator's degree is smaller than the denominator's degree, the x-axis is a horizontal asymptote. So y equals 0 is my horizontal asymptote. And again, if you pause and ponder this for a minute, and you look at the function g of x, what happens as x gets infinitely big? As x gets infinitely big, that denominator gets infinitely bigger than the numerator because you're squaring a big number, multiplying it by 3 and adding 1. The plus 1, who cares? But the denominator is increasing at a much faster rate than the numerator. And what happens if a denominator gets bigger and bigger and bigger and bigger and bigger? The entire fraction, as the denominator gets larger, approaches 0. So as your denominator gets bigger, your fraction gets closer to 0. So since we have a numerator exponent is smaller than the denominator's exponent, the x-axis y equals 0 is our horizontal asymptote. Okay, the two basic reciprocal functions that they give you in this book are 1 over x and 1 over x squared. So the function f of x equals 1 over x, it has a vertical asymptote at 0. So x equals 0, the y-axis is a vertical asymptote. It also has a horizontal asymptote at y equals 0. The x-axis is a horizontal asymptote because the numerator's degree of that function is 0. The denominator's degree is 1. 1 is bigger than 0, so y equals 0 is the horizontal asymptote. 1 over x squared also has a vertical asymptote at x equals 0, horizontal asymptote at y equals 0. And you can see what that function looks like. So just like in chapter 1, section 5, where we transformed functions, or was that chapter 2, section 5? Whatever chapter it was, whatever section it was. We transformed functions. I do remember that. And how did we transform them? We added a constant to x, the input of our function, and that transforms it horizontally. So if we add a constant to x, that moves it to the left. If we subtract a constant from x, it moves it to the right. And if we add a constant to the function, the f of x, that moves it up. And if we subtract a constant, it moves it down. And then if you multiply stuff by negatives, it reflects it about the x-axis. So just like before, you can take one of these reciprocal functions and you can transform it. So if we take the reciprocal function 1 over f, 1 over x, f of x equals 1 over x, and we add a 2 to the x, which we did right here, and then we subtract 1, we get a new function, g of x. So g of x is 1 over x plus 2 minus 1. Well, what does that do to this standard reciprocal function? Well, the plus 2 does what? Moves it 2 units to the left. And what's the minus 1 do? It moves it 1 unit down. Well, it moves everything, absolutely everything. So it takes that vertical asymptote at x equals 0 and moves it 2 units to the left. So the entire graph gets shifted to the left, including the asymptote. And the -1, you're going to shift everything down 1, including that horizontal asymptote. It gets moved down 1. So now the vertical asymptote is at x equals -2, which makes sense if you look at the equation of this function. And the horizontal asymptote is -1, which also should make sense to you, because as x increases without bound, as it gets infinitely bigger, what happens to the 1 over x plus 2? It becomes 0 as x gets infinitely big. So what are you left with? -1. So our vertical asymptote is now at -2, horizontal asymptote is now at y equals -1, and everything else gets shifted also. All the points get shifted, everything gets shifted. All right. All right, graphing a rational function. Here's the strategy that my math lab uses, your author uses. First, check for symmetry. Replace x with -x and see what happens. 99.9% of the problems you are going to do not have any symmetry. Then find the y-intercept, find the x-intercept, find any vertical asymptotes, find any horizontal asymptotes if there are any. There may not be, but if there are, find those. Plot at least one point beyond the x-intercept and the asymptotes, and then graph the function. Now you're going to be choosing a graph from multiple choice. So I do suggest you graph it on your calculator and match the window, the X window and the Y window on your calculator to what's in my math lab. But the rest of these questions you have to answer in my math lab. So let's graph this. The first thing we do is check for symmetry. So I'm going to evaluate this function at -x. That's how we check for symmetry. So wherever there's an x, I replace it with a -x. And I'm thinking I'm going to factor a negative from the numerator and the denominator so I can cancel that. Those cancel. And so I end up with f of -x is equal to 3x plus 3 over x plus 2. Okay, is that equal to f of x? No, that is not what I started with. So there's not symmetric about the y-axis. Is that equal to negative f of x? Exactly the opposite of what I started with. What would be exactly the opposite of this, what I started with? That would be only if the numerator changes sign. The denominator would be the same. So is the numerator negative 3x plus 3? And the answer is no. So there's no origin symmetry. You could also graph this and see that there's no symmetry with respect to the y-axis or the origin. Okay, the next thing you're going to do is find the y-intercept. To find the y-intercept, you evaluate this function at 0. So wherever there's an x, replace it with a 0. So we get -3 over -2. That is 3/2. So the y-intercept is 3/2. Find the x-intercept. To find the x-intercept, you set the numerator equal to 0. Because that is where this fraction is 0. A fraction is 0 when its numerator is 0, not when its denominator is 0, when its numerator is 0. So x equals 1 is the x-intercept. Now I do need to pause and make sure that that is not a restriction on the domain of this function. and it looks like the restriction on the domain is 2, not 1. So I think we're okay that that's the x-intercept. You do need to make sure your x-intercept is not a restriction on the domain of your function, that it's not an asymptote, vertical asymptote, or a hole in the graph. All right, the next step is to find the vertical asymptote, and I did not factor this. I am going to factor it real quick. There's no common factor in the numerator and the denominator, nothing I can cancel. So I set the denominator equal to 0. X equals 2 is my vertical asymptote. Now, horizontal asymptote, the numerator degree is 1, the denominator degree is 1. Both exponents on those x's are 1. So what are your rules for horizontal asymptotes? If the degree is the same, go back and look at the rule. It says that if the degree is the same, then there is a horizontal asymptote that is a ratio of the leading coefficients. There's an understood 1 in front of that x. So 3/1 or 3 is our horizontal asymptote. And that should kind of make sense to you, that if as x gets increasingly big, the -3 and the -2 become negligible as x gets infinitely big. So all you would have left is that ratio of 3/1. All right, so now we go and we plot all that stuff. Plot the x-intercept, plot the y-intercept, draw the vertical asymptote at x equals 2. And so now they say, okay, then I want to plot some points on to the left of the x-intercept and maybe some points to the right of that asymptote. So I'm going to evaluate this function at -1, at 1/2, at 3/2, at 5/2, and 3. Do not get this wrong. You have a calculator. Do not let evaluating a function be the reason you get a problem wrong. Use your calculator. Okay? There's a couple of different ways you can do this. I mean, I can certainly plug in -1 for x and then do that on my calculator. 3 times -1 minus 3 divided by -1 minus 2. I can do that. You can graph it and then use the table. You can graph it and use value, evaluate it at a value. There's a million ways you can do this correctly. Don't do it incorrectly. So if you evaluate this function at -1, you get 2. If you evaluate it at 1/2, you get 1. If you evaluate it at 3/2, you get -3. This table here in this problem, I am yelling at you. Don't get that wrong. You have a calculator. Let your calculator do it. Okay, so now we're going to graph this thing. So we have x-intercept at 1. I better put my glasses on so I can see. And I don't have my axis labeled, so let's put a quick label on here. My previous graph didn't have enough points on it, so I got another graph. All right, that may be enough. Okay, so what do we have? We have an x-intercept at 1. We have a vertical asymptote at 2. So let's draw that in. We have a horizontal asymptote at 3. Let's draw that in. That'll help us get an idea of what this looks like. We had a y-intercept at 3/2, 1.5, right there. And then we have a few points we can plot. At -1, we have 2. At 1/2, we had 1. So I think I got an idea of what it looks like over here. It looks like it's going to do this, doesn't it? as it goes to negative infinity, my graph is going to approach that line y equals 3. And as we come to that vertical asymptote at x equals 2, we're going to decrease without bound. Okay, so let's plot some points over on the other side of that vertical asymptote. Now, you are not going to have points over here. Okay, you're not going to have points over here. You're probably going to have points above that horizontal asymptote. So let's go ahead and plot a couple of points. We had 5/2, 9. So 2.5, 9. 6, 7, 8, 9. 2.5, 9 up here. And then we had 3, 6, 3, 6. So it looks like it's doing this. So as it's approaching from the positive direction, as it's approaching the line x equals 2, it increases without bound. That's the vertical asymptote. And as x goes to infinity, it gets increasingly big. Then the function approaches that line y equals 3. So that's a really terrible graph, but that's what it looks like. Okay, slant asymptotes. This is the case if the numerator's degree is exactly 1 more than the denominator's degree. So the numerator's largest exponent is exactly 1 more than the denominator's, then that is a slant out. It has a slant asymptote. And the way you find the slant asymptote is to do the division. And the slant asymptote is the quotient. So I don't care about the remainder. All I care about is the quotient. So I'm going to do this division. I'm going to use synthetic division because I'm way out of time and it's just so much faster. And at this point, I'm done. I don't really need to find the remainder. That's the remainder. Well, the slide's being slower than my. There, it got up. So all I'm really concerned with is the quotient. So if I set y equal to whatever that quotient is, that is the slant asymptote. So that's going to be what? 2x minus 1. So the slant asymptote is 2x minus 1. So if the numerator's degree is 1 less than the denominator's, you find the slant asymptote by doing the long division, doing the division. And whatever your quotient is, set that equal to y, and that's your slant asymptote. Y equals your quotient is your slant asymptote. Okay, and then there's the graph of it. Okay, polynomial and rational inequalities. You need to be able to do this for calculus. That's where we use this. So how do you determine the solution to a polynomial or a rational inequality? Well, you have to have it in the form of f of x is greater than 0, less than 0, greater than or equal to 0, or less than or equal to 0. So what you're interested in is where this function's negative if it's less than 0, or where this function's positive if it's greater than 0. So you're interested in looking at where y values are positive or negative, because you're looking at where this function's either negative, the value of the function, or where it's positive. So you're going to have a solution that is an interval of numbers. You're going to have interval solutions, not point solutions. So how do you do this? You first set it up so that the function fits this form. You either have 0 on the right-hand side and less than, or you have 0 on the right-hand side and greater than, one or the other. Then to find these things we call boundary points, you set the function equal to 0 and solve the equation. then those numbers break your number line into intervals. So you're going to draw your number line and you're going to create these intervals because the solution to this is an interval solution. Then you pick a test point in each one of these intervals. So pick a number that's in that interval and evaluate the function. If the function's positive, then it satisfies greater than 0. If it's negative, then it satisfies less than 0. And then you write your solution. All right, let's do an example. Oh, by the way, if it's greater than or equal to or less than or equal to, the endpoints are included in the solution. So you use brackets on anything that makes the function equal to 0. All right. So let's solve x squared minus x is greater than 20. So the first thing you do is you move that 20 over, because I have to have it in the form where I'm greater than or less than 0. So I have to have it in this form. Then you solve this equation. I'm going to do it by factoring. So I have these two boundary points. Boundary meaning they separate my number line into intervals. So I have a boundary point at -4 and a boundary point at +5. So I'm going to go quick, draw my number line. And I have a boundary point at -4 and a boundary point at 5. So this breaks my number line up into intervals. And what are these intervals? Everything to the left of -4, everything between -4 and 5, and everything to the right of 5. So those are the three intervals that my number line is broken into because of these boundary points. And then I pick test points in each of these intervals. So go to the first interval. Give me a number that's less than -4. I'm going to pick -5. Then go into the interval between -4 and 5. Pick a number that's between -4 and 5. I'm going to pick 0. And then pick a number that's bigger than 5. I'm going to pick 6. I'll put those up here. And then you are going to evaluate your function at each of these values to see if it's positive or negative. So here are my intervals. That's a 4. Here are my test values. And then I'm going to evaluate the function. So I'm going to evaluate it at -5. Don't get this wrong. Your calculator can do this. So -5 squared is 25. 25 plus 5 is 30. 30 minus 20 is 10. So your function is positive in that interval. If it's +10, it's positive for every number in that interval. So if it's positive for your test point, it's positive for every number in that interval. Okay, how about at 0? So for every point in that interval, it's negative. Okay, how about at 6? 36 minus 6 is 30. 30 minus 20 is 10. That's positive. So where is this function positive? Because our original function was greater than. I don't know why I've got the equals there. It's greater than right there. So where is it positive? It's positive from -∞ to -4 and from 5 to infinity. So what's the solution to this inequality? Any number less than -4 or greater than 5. So your solution is all right. So what if It's a rational inequality. Well, the same rule applies. You have to have it in the form greater than 0, less than 0, greater than or equal to 0, or less than or equal to 0. Okay, so that's not the form that this one's in. The vast majority of your problems, you'll be given it to you in the form where you have 0 on the right-hand side of the inequality. I'm going to real quick, for time, go ahead and get this in the correct form. So I'm going to subtract 1 from both sides. I'm going to get a common denominator. Okay, so now I have 2x minus 1 times x plus 1 over x plus 1 greater than or equal to 0. So I have 2x minus 1 over x plus 1 greater than or equal to 0. So I have x minus 1 over x plus 1 is greater than or equal to 0. So I am interested in where that function is going to be a positive number. Now I have greater than or equal to, and a fraction's only equal to 0 at when the numerator is 0, not when the denominator is 0, when the numerator is 0. So I am going to include any endpoints that make my numerator equal to 0. Okay, so how do you find the boundary points when you're solving a rational inequality? To find the boundary points when you're solving a rational inequality, you set the numerator equal to 0 and you set the denominator equal to 0. So set the numerator equal to 0, set the denominator equal to 0. So we get x is 1 and x is negative 1. So our boundary points are 1 and negative 1. So my intervals are going to be from negative infinity to negative 1, negative 1, negative 1 to 1, and from 1 to infinity. And then I'm going to talk about where do I use a bracket or where do I use a parenthesis. I cannot use a bracket next to negative 1. It's got to be a parenthesis. Because if x is equal to negative 1, the denominator is negative 1, and I can't have that. But I am going to put a bracket next to 1. Since my inequality is greater than or equal to, I include the endpoints that make the numerator equal to 0. Do not include the endpoints that make the denominator equal to 0. Include the endpoints that make the numerator equal to 0. Okay, so now I'm going to pick some test points. I need a point that's smaller than negative 1. How about negative 2? Pick a point between negative 1 and 1. I think that would be 0. Pick a point that's bigger than 2. And you're going to let your calculator evaluate this function for you. Don't stress about this. You have a calculator that can do this for you. Okay, so what test values did I choose? I chose negative 2. I chose 0, and I chose 2. Okay, so my intervals are from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. My test values are negative 2, 0, and 2. My function evaluated at those points are f of negative 2 would be negative 3 over negative 1. That would be 3. That's positive. Evaluate the function at 0. I get negative 1 over 1. That's negative 1. That is negative. Evaluate this function at 2. I get 1 over 3. That's 1/3. That is positive. So where is this function positive? It's positive from negative infinity to negative 1. And it's positive from 1 to infinity. It's negative between negative 1 and 1. So again, bracket next to the 1 because 1 is what makes the numerator equal to 0. Parenthesis next to -1 because -1 has a restriction on the domain. It cannot equal -1. Why do I put a bracket next to the 1? Because my inequality is greater than or equal to. If my inequality is greater than or equal to or less than or equal to, I will be using brackets somewhere. Because I could have somewhere where my function's equal to 0. All right, variation. 18 minutes to cover variation. Actually, that might not be too bad. We're going to look at direct variation, inverse variation, combined variation, and joint variation. And all of these problems work exactly the same way. You set up the equation, you solve for the proportionality constant, the constant of variation, plug that back in, and then you have an equation. Okay, so if you have a situation that's described by an equation in the form y equals k times x, so you have two variables, y and x, and the only difference in those variables is a factor of k. K is a non-zero constant, so it is a constant, and we say that y varies directly as x or y is directly proportional to x. So if your variables are on the same level and they only differ by a constant, that's direct variation. And k is the constant of variation or the constant of proportionality. So you're going to be given a word problem, and they're going to say, velocity varies directly as time, something like that. I don't know. And you're going to write the equation, the variation equation. And then they're going to give you the two variable values. They're going to say, you know, the velocity is 10 miles an hour when the time is 2. You plug that in, you find k. Once you have k, the proportionality constant, you plug that back in, you get an equation, and then you have an equation that you can use to find any value of y given x. Okay? So the number of gallons of water W used when taking a shower varies directly as the time. So the amount of water you use varies directly as the time. So your equation is W equals K times T. Then the next statement will give you a W and a T, so you can find K. A shower lasting 5 minutes uses 30 gallons of water. So when W is 30, T is 5. So K is 6. How much water is used in a shower lasting 11 minutes? So now we can write the equation. The equation will be W equals 6 times T. And now if T is 11, you use 66 gallons of water. So we write the equation. So when T is 11, W equals 6 times 11, which is 66 gallons. And they all work the same way. Whether it's direct variation or inverse variation or joint variation or combined variation, they all work the same way. So variation with powers, you could have direct variation, but your x could be raised to a power. Okay, so something like this. And I always ask my classes, have you seen the movie Jaws now? And they're talking about the book. Have you read the book Jaws? Yes, when I was young, I read the book Jaws. And I also have seen the movie. The weight of a great white shark varies directly as the cube of its length. So if I use W for weight and L for length, I can write an equation. So weight varies directly as the cube of its length. So W equals what? K times L cubed. We're cubing the length. All right, what else do we know? A great white shark caught off Catalina Island, California, was 15 feet long and weighed 2,020 pounds, 2,025 pounds. So I can put in 2,025 for W and 15 for L and find K. Then what do they ask me? What was the weight of the 25-foot long shark in the novel Jaws? Okay, so the first thing we need to do is find K. So we have W equals K times L cubed. And we know that a 15-foot long shark weighs 2,025 pounds. So we make those substitutions. And I'm going to cube 15. And when I cube 15, I get 3,375. So K is 0.6. So my equation is W equals 0.6 L cubed. And so how much does this 25-foot shark in Jaws weigh? So take your handy dandy calculator out, multiply 0.6 times 25 cubed, and I get 9,375 pounds. That's a big shark. All right. Right, inverse variation, your variable X will be in the denominator. So the way this is described is Y varies inversely as X. The length of a violin string varies inversely as the frequency of its vibration. So length varies inversely as frequency. L equals K over F. A violin string 8 inches long vibrates at a frequency of 640. So multiply both sides by 640. And we get K is equal to 5,120. What's the frequency? Oh, they're changing it up a little bit. What's the frequency of a 10-inch violin string? So what's my equation going to be? My equation is going to be the length is 5,120 divided by the frequency. So I could solve this for F by multiplying both sides by F. I don't know why I did that. And dividing both sides by L. So I get F is equal to 5,120 over L. So the frequency can be found by taking 5,120 and dividing it by the length of the string. So our string was what? 10 inches long? So a 10-inch violin string vibrates at 512 cycles per second. All right, so inverse variation. We've had direct variation to a power, and then inverse variation. So what's our next variation? Next variation is combined. And this is where you have one variable varying directly as another variable and inversely as a third. So now you have 3 variables. You're varying in directly, 2 are varying directly, and then inversely to the third one. The number of minutes needed to solve an exercise set of variation problems varies directly as the number of problems and inversely as the number of people working to solve the problems. Now I might use X, Y, and Z for this because I've got problems and people, minutes. I don't know. I don't know what variables I'm going to use. It takes 4 people 32 minutes to solve 16 problems. How many minutes will it take 8 people to solve 24 problems? So let's let M be the number of minutes it takes. And maybe I'll let N be the number of problems. And maybe we'll let P be the number of people. I could have just as easily used X, Y, and Z, whatever you want to use. Okay, so what do we know? The number of minutes needed to solve varies directly as the number of problems and inversely as the number of people. Go back. So we have M equals Kn over P. And they tell me, what do they tell me? It takes 4 people 32 minutes to solve 16 problems. So when P is 4, M is 32, and N is 16. So I can plug all those numbers in and find K. So I'm going to go to the next slide and do this. So let me rewrite it. So we have M equals Kn over P. And we have the number of people is 4. The number of minutes is 32. And they're going to solve 16 problems. So let's make those substitutions. 32 equals K times 16 over 4. So divide both sides by 4, and I get K is equal to 8. So my equation is M equals 8 N over P. Okay, so now what do they want to know? I didn't write that down on this slide. How long will it take 8 people to solve 24 problems? So if I have 8 people and 24 problems, how many minutes is this going to take? Is that 24? All right, so that is combined variation, where 2 of the variables vary directly and 2 of the variables vary inversely. A joint variation is a variation in which a variable varies directly as the product of 2 or more variables. Thus, the equation y equals k times x times z is read by y varies jointly as x and z. The volume of a cone, it's a terrible drawing of a cone, varies jointly as its height. So this is its height. And the square of its radius. So the radius is the radius of this part right here. It's that distance right there. That's the radius. Terrible drawing. A cone with a radius measuring 6 feet and a height measuring 10 feet has a volume of 120 pi cubic feet. Find the volume of a cone having a radius of 12 feet and a height of 2 feet. So it tells me that the volume I am going to use, and they told me it's V, varies jointly as the height, K times H, and the radius squared. So volume is K times H times R squared. All right, and then they tell me that a cone having a radius of 6 feet and a height of 10 feet has a volume of 120 cubic feet. So we're going to make those substitutions. 120 pi for the volume, 6 feet for the radius, and 10 feet for the height. And we're going to find K. So we're going to plug all that in and solve for K. So I have 120 pi equals K times the height, which is 10, and the radius, which is 6 squared. So 120 pi equals K times 10 times 6 squared. So 120 pi is equal to K times 360. 36 squared is 36. 36 times 10 is 360. Divide by 360. And we're going to just reduce this fraction. $120 will go into 360 3 times. So K is pi over 3. And this is the equation or the formula for the volume of a cone. The volume of a cone is found by taking pi over 3 times the height of the cone times the radius of its base squared. So the volume of a cone is pi over 3 HR squared. That is what it is. That's what the formula. You can Google it and it will tell you that's the volume of a cone. Okay, so what do they want you to know? They want you to find the volume of a cone whose height is 2 feet and whose radius is, what was the radius? 12. So we're going to just plug and chug. So the volume will be pi over 3 times 2 times 12 squared. So that's going to be pi times 1 times 2 times 144 divided by 3. And you could take your handy dandy calculator out and calculate pi times 2 times 144 divided by 3. And I get 96 pi. So the volume in terms of the number pi is 96 times pi. Now your calculator has a pi button. So you can take 96 times, and that's above your power button. So it's above the caret. So you take 96 second caret, enter, and it will give you a decimal approximation for that volume. And I'm done, 9:15.